Hi, and welcome to my channel, JaberTime, where I do math videos for all levels, from algebra to calculus and differential equations, simplified with examples. I'm also adding videos on apps and programs to help students and teachers alike, enhancing the learning and teaching online. If you're new here, welcome, and consider subscribing and hit that like button so that I know that you enjoyed this video. And also let me know in the comments below if you have any questions. I do upload a video or two every week, and I'm so excited about converting all my math notes from teaching over 25 years into simplified YouTube videos with examples. Once again, thank you for being here and hope to see you again and again. Alright, let's get into it. Limits Part 4. We're going to talk about continuity. The main formula and definition of continuity is limit f of x as x approaches a equals f of a itself. This is the graph that explains it all. You could see from the graph that I'm saying a is defined at this point and the value is f of a. As you approach a from the left, as x approaches a from the left, you are going up on the curve this way. So you are approaching this point. So the limit from the left is actually also f of a. And when you approach a from the right, we write it as x approaches a from the right. Notice in blue here that you are on the curve coming down, approaching the same dot. So the limit of f of x as x approaches a from the right is also f of a. So what we have here is continuity at a point, this point a. A function f is continuous at point a if the limit of f of x as x approaches a, which means left and right, both, is the same value, exactly the same value as f of a, and the graph shows it all. How do you check for continuity in steps? In order for f to be continuous at point a, the following three conditions must hold. And still we're looking at the graph because it explains it all. Number one, f of a is defined. This cannot be an open circle, cannot be empty. It has to be defined. Well, that's the meaning of the word continuity. If it's continuous, how would you call it continuous if it's not connected? If this part here and this part here are not connected at this point, they are two pieces. That's kind of like, it doesn't add up. So anyway, f of a has to be defined. The limit also has to be there. It has to exist as x approaches a itself. Not only that, well, if you are here approaching 7 and here you are at level 5, you cannot say that it's continuous. But the graph says a f of a, and you are approaching from right or left, you are still approaching the same amount. So f of a and approaching a from both sides should be the same amount. And that's part 3. So limit f of x as x approaches a is exactly what we're looking for, which is f of a. Let's look at a graph that explains more with numbers. See this graph right here? It's not defined when x equals 0. There's an open circle right here. It's connected here, and coming down here is connected, and this one is filled. After x equals 2, you're gonna have to jump to the right side of this circle. That's called jump. And when you go down, you're going down to infinity, but it looks like you cannot reach a value of x equals 3. Once you pass 3 to the right side, you're going to be on this curve, the right side curve. Same thing, you're going to go up. This is empty, that's not connected, and we're using the word continuity, and it's defined somewhere else. Then after I pass 4, if I'm right here, f of 4 is 3, I'm going to jump here and come back down here. And also it's not defined when x equals 5. So we have issues or concerns when x equals 2, when x equals 3, and when x equals 4. So f of x is discontinuous or not continuous at the 3 points that I mentioned, x equals 2, 3, and 4. Let's discuss one by one and what's the reason behind it. Remember the checklist 1, 2, 3? We're gonna decide each one is what's happening. Is it mainly the concern about step 1 or 2 or 3 from the checklist? So let's look at x equals 2. When x equals 2, I could see it's defined. I could see the limit from the left is the same, but the limit from the right is higher at 5. And everything is written here for your convenience. F of 2 is defined at 3. The limit as x approaches 2 from the left is also at 3. The limit from the right side as x approaches 2 from the right is all the way up to 5. Well, these two, they are saying that the limit does not exist, and I could see that. Clearly from the graph, the limit does not exist. From the right and left, there is a big difference, so we call it does not exist. So, that's the reason why we have discontinuity at x equals 2, because number 2 says the limit has to exist, but here it does not exist. Let's look at 3. Before I see the notes or show you the notes, at 3 there's a problem. First of all, it's not defined at 3 and the limits are down. So here we go. X equals 3. F of 3 is not defined. Case closed. That's number 1. We don't have to look at the limits from right and left, which is down to negative infinity, but that's not our concern anymore, and we're done. Besides, you know what? Limit as x approaches 3 is negative infinity. Negative infinity is not a number. So it's not something that you say, oh, my limit is so and so. The limit has to be L, which means a number that you could point at. So that's not what we're looking for. Let's look at number 4. Number 4 from the left is the same thing as from the right, but at the same point it's not the same. At f of a is not the same. So let's reduce some time, because I don't want to keep explaining myself and make the video lengthy. I'll do my best to deliver notes highlighted to the best, and I'll try to speak slower and less. So we have f of 4 is 3. The limit from left and the limit from right is the same as 5, leveled all the way up. So the limit does exist and it's defined at 5, but 1 and 2 should be equal, but they're not. So when you look at the checklist 1, 2, 3, 1 is fine, 2 is fine, 3 saying that these two should be equal, but they're not equal in our case. Clearly the graph shows it. Hopefully my notes are so clear about what is discontinuity and what's continuous. As you could see, different examples in one graph. Alright, let's look at continuity on an interval, not at a single point. Well, if it's continuous at an interval, it has to be continuous at every single x in it whenever x changes from a to b to c and so on. So a is just like a generic thing to refer to. A function y equals f of x is continuous on an interval I if the graph of f of x has no holes, no jumps, or breaks. We say that a function f is continuous at a given point A if the graph of f does not have a hole or break at A. The last graph was showing that also. That is if the graph near A can be drawn without lifting the pencil. That makes total sense. So if you trace it, you're not going to be lifting the pencil to jump to another piece, and you can just keep going through it smoothly. Let's look at polynomial and rational functions. In rational functions, we have a special case. We have to look at the denominator. So let's take a look at it. A polynomial function is continuous for all x. So if we have, for example, y equals 5x to the second plus 2x plus 7, that's a parabola second degree equation. You know how it looks like, and you know it's a smooth curve. So we don't have any issues with polynomials. Polynomials are nicely graphed, and they're always continuous. So that's a fact. A rational function is actually, or overall, is a polynomial on top and a polynomial at the bottom side. So we call them in short P and Q, where P and Q are polynomials. Will be continuous if it's a rational function for all x, such that the denominator q of x is not 0. Well, you know that because we can't have 0 anyway in the denominator. So anything that forces the denominator to be 0 will be out of our domain because we cannot use that. Continuity at endpoints. This is something that we have to clear. That's why I have the notes for you. A function f is continuous from the right or right continuous at a if the limit of f of x as x approaches a from the right is exactly the same as f of a. Notice we're not looking at limit f of x as x approaches a from the left. Okay? With these notes, I don't want to confuse you. I have two graphs for these ones, this one and the one coming next to it right here, to show you what I mean. So you could go back to it anytime you want. The other way around, this is called right continuous. We're going to talk about right continuous. F is continuous from the left, or left continuous at b if limit f of x as x approaches b from the left is f of b. Let me explain through a graph. Graphs do help a lot understand concepts and definitions, so let's take care of it. Continuity on an interval, that's our topic. This here is defined from a to b. A is included, part of my game, part of my domain. B is out of my domain. Continuous on closed interval at a all the way to b, not including b. When you approach a, you approach it from the right. That's called right continuous at a. Let me take you back. You see this right here? That's called right continuous at a. So you're approaching a from the right. And not only that, you have a value for that, and it's equal to f of a. Let's move forward. F of a is this much, which I don't have a value for it now. I could call it f of a, but I forgot. Approaching a from the right, you're going to approach the same point. And that's what the note says. Same thing for left continuous at b. So when you approach b, you're approaching this way, approaching b from the right side. And this will be defined as f of b. This part here is f of b, the value when x equals b. And the limit as x approaches b from the left. See, from the left. We are approaching it from the left of it. We are not on the right and we cannot be there. Is the same as f of b. Now, let's go to trig functions. In trig functions, I can't cover them all here and call it a video or lecturing online, but at least gives you an idea about where to pay attention to and be aware of. I have two graphs in one right here. Basically, we're going to discuss secant x, which is defined to be 1 over cosine x. So cosine x is graphed in green, and it's graphed more than one period. One period will be going from this point down all the way back up. But because I'm concerned about secant, I continued to show you this piece as one piece. All right. So at this point, cosine is up to 1. This is 1. All right. 1 over cosine, 1 over 1 will be still 1. So at this point, it belongs to the green graph. It belongs to the red graph, which is secant. When x is moving between 0 and pi over 2, cosine gets smaller, because on the unit circle, the x distance of the coordinates, or the point that moves on the circle counterclockwise, represents cosine, and cosine starts at 1 and moves closer to the y-axis, so it gets smaller and smaller and smaller. So for example, if this is like, let's say 0.5, if cosine is limited at 0.5, 1 over 0.5 is actually what? 0.5 is half, 1 over 2. 1 over 1 over 2 will be flipped again, and it's going to be 2. So if this is 0.5, that's going to be 2. All right, that's why the graph of secant looks like this. Let's move on in more details about the graph and try to cover the best in less time. So secant x is continuous at all points of its domain. But what's its domain? Well, here's a piece here. Here's another piece here down here. They're not connected. Here's a third piece, as my graph shows. Here's a fourth piece, and here's a fifth piece. So it's pieces disconnected. So between them, there's vertical asymptotes, the blue dashed lines, as you could see. Well, that is defined for all x except when x equals plus minus pi over 2, plus minus 3 pi over 2, plus minus 5 pi over 2. Pi over 2 plus minus 3 pi over 2 plus and minus 5 pi over 2 plus and minus. Or differently, we could say odd multiples of pi over 2. 1 pi over 2, 3 pi over 2, 5 over 2. Odd multiples will cover both plus and minus. Notice that cosine x equals 0 at these points. It's not defined. Cosine x equals 0, which means 1 over 0 is not defined. That's why we have vertical asymptotes. We talked about that in the previous videos, that when the denominator is 0 and nothing cancels that factor, we do have vertical asymptotes. Okay, I think that's good enough. It's not everything about trig functions, but it gives you an idea. Let's move on to more algebra of polynomials and some examples. Here's an example. P of x over q of x, we're still in rational functions. My polynomial on top is 2x squared plus 3x plus 1, and down here it's x to the second plus 5x. To find the discontinuity points, we need to find the zeros of q of x, the values of x for which the denominator of f of x is 0. That's what discontinuity happens. Zeros of the denominator, because we cannot be there and it's out of my domain anyway. So let's take q of x, which is this part, and set it equal to 0. X to the second plus 5x equals to 0. Factor x out using the principle of zero products. I get two values, x equals 0, or what forces this to be 0, which is x equals -5. Now, the domain of this right here, on top it's all real numbers, down here everything all real numbers except 0 and -5, because we do have a problem here going back to f of x having these numbers. So the domain of f of x is all real numbers except, that's one way to write it down, -5 and 0. So the function f of x is not continuous at these points because they're taken out of my domain. So it's continuous everywhere else that is on its domain, which is all real numbers except -5 and 0. Here's another example. It's a piecewise function, two pieces. Not only that, the first part is rational function. Now, before I start, let's take this and simplify it on the side. X to the second minus 1 over x minus 1. The top part is a difference between two squares. Factors to x minus 1 and x plus 1. Notice x minus 1 cancels. Do you remember this? Whenever you have a factor like this cancels, we have a hole in the graph. But this what stays with me, so I wrote it down x plus 1. So this part right here is simplified to be x plus 1 when x does not equal to 1, which is why that's why they have it right there. You could approach 1, but you can't use 1. As a limit, you could approach 1, plug in numbers here like 1.001 or 0.9999, but you can't plug in 1, because if you plug in 1, you have a problem in the denominator, and it's not defined, it's taken out from this part right here. So looking at this part, it's actually, if you graph it, if you type it on a graphing calculator, it's actually a straight line. Straight line with the slope of 1 and the y-intercept of 1. But when x equals 1, there's a gap in the graph. Graphing calculators won't show you the gap or the opening unless if you have the right settings on the calculator. But if you need help on that, just leave me a comment below and I'll help you see it if you need to. So let's move on. When x equals 1, remember the checklist? We start with f of a equals, or defined. That's f of 1, which is 3, defined. Okay, that's fine. So far so good. The limit from the right and left, we're still here. We're not using right and left because that covers both. This is our rational function, simplifies to x plus 1 as we saw earlier. Plug in 1, you get 1 plus 1, which is 2. But that's a problem. On the checklist, number 1 says f of a is defined, exists. On number 2 it says the limit exists. Okay, so far. Number 3 says they have to be equal, but they're not equal. So the limit of f of x as x approaches 1 does not equal to f of 1, because the limit on the left side right here is 2 and f of 1 is 3. So f of x is not continuous at x equals 1. Let's take another rational function. X to the fifth plus 6x plus 17 over x to the second minus 9. We always focus on the denominator for continuity. This is my q of x, difference between two squares, and we could factor it and find the zeros. So here we go. X minus 3 and x plus 3, difference between two squares. So the denominator q of x is x squared minus 9 equals 0 when x equals negative 3 and when x equals 3. F of x is not defined at these values. F of x, which is a rational function in our case, is continuous on its domain. This time I wrote it differently because you need to see different ways of writing the domain or the continuity region. That is from negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. Notice that those are open intervals. Those are not order pair. Those are intervals. So here you stop at negative 3, but negative 3 is not included, and here you start from negative 3 without including negative 3, and you go up to 3. 3 also you stop not including it, and you go. So that's another way to write it down. Let's take another example. This is a different one, so let's take a look how we could do it. This is with a power on top. How do you handle it? Earlier we have it as a rational by itself. Now this one with a power. So what you do inside, you simplify to the best that you can. 2x plus 1 over x, you divide top and bottom side by x as we explained in previous videos. 2x over x will be 2. 1 over x will be 1 over x. That's one way to do it, or just divide, which is called distributive. Now, we're gonna walk in and apply the limit inside. The limit of 2 is 2. The limit of 1 over x as x approaches infinity is 0. So it's 2 plus 0, which is 2 to the third. That's 2 to the third, which is 8. Done. That's it. Next example. Piecewise function. To the left of 2, you are at 3x. To the right, including 2, to the right of 2 including 2, it's 5x plus 1. Let's see if these two line segments or these lines, they meet when x equals 2. If not, they're going to be a jump. First of all, f of 2 equals 11. Why is that? Well, you see the equal sign right there? I have to use this because I belong to the second piece. It's right there. Now, from the right side, that's f of 2 equals 11. From the right side of 2, I'm still there. The same piece. That's right there. When you are to the left of 2, approaching 2 from the left, you should be using 3x, not 5x plus 1. And that's right here. Approaching 2 from the left, I should multiply 3 times x, which is, in this case, I have no problem to write 3 times 2, which is 6. But the limit from the right is 11, and the limit from the left is 6. That is what we say the limit as x approaches 2 does not exist. So this function right here has a jump, and it's not continuous at x equals 2. We're almost done, by the way. Let's move on. We have f of x is continuous on its domain, or real numbers. Actually, not in the domain. I'll take it back. I was thinking about rational functions for a second. I'll take it back. F of x is continuous on all real numbers except 2. If you graph it, you'll see the jump. It's two pieces, one to the right, one to the left. Of 2. Okay. Let's write this differently, as I did in the previous example. So f of x is continuous on negative infinity to 2, not including 2, union 2 to infinity, not including 2. So it's defined all the way from negative infinity to infinity, but not including 2. That should do it for this video. I did my best to not to make it 45 minutes or 41 minutes or whatever. It's about probably like 28 minutes. That should do it. If you have any questions, please leave them down below. After I post the video, I go through it and I see the timeline, where's my examples starts, and I add the timeline in the description, time for every single example and what type of example I'm going to be covering. So make sure you look at the description for my videos from now on. They do help. And if you want to stop the video on any screen, I said that before and I'll keep saying it, just hit the space bar. And if you want to move back to play mode, just hit the space bar again. So the space bar acts like a remote control. You just stop it whenever you want with a click, and another click will move it on. That works on both PC and Mac. Thank you. Thank you for watching. Subscribe and hit the like button if you did like this video. If you have any comments or questions, leave them down below and I will get back to you. And I'll see you next time.